Hello everyone, as usual, I hope you and your families are remaining well. What I'm going to do in the next couple of videos, next three videos, is three problems from section 3.3. So what I'm going to do is keep this chart open, this chart up on the board, and I'm going to do number 24, and then I'll stop the video and we'll go to probably problem 31, and then problem 34. So let's get started on this one. What's different about these problems, they all involve this information. This is the information you have to know. You have to realize that if the first derivative is positive and the second derivative is negative, that means the function is increasing and concave down. Concave down because the second derivative is negative, increasing because the first derivative is positive. If the first derivative is positive and the second derivative is positive, our function is increasing and concave up. If the first derivative is negative and the second derivative is negative, we have a decreasing function, concave down. If the first derivative is negative and the second derivative is positive, we have a decreasing function that's concave up. Notice also that if the second derivative is negative, that means the first derivative is increasing. If the second derivative is, I think I said that right, the second derivative is negative, that means the first derivative is decreasing. If the second derivative is positive, that means the first derivative is increasing. What you have to know, where f prime and f double prime are 0, those are the places where we can switch. Those are the only places we can switch from where the first derivative could switch from positive to negative or negative to positive, where the second derivative could switch from negative to positive or positive to negative. And those are exactly the places where the function has local maxima, local minima, and inflection points. But this is the heart of the information that you need. This is what you apply over and over again in these problems, but in different ways. And I wanted to do several problems that require you to apply the information a little differently. So on problem 24, there are a slew of problems that say, draw a graph of a function that satisfies all these conditions. And I love these because it really challenges you to think about what these conditions mean and what you need to do. So the problem says the derivative is positive, greater than 0, on everywhere. Okay, so we know the function is always increasing. It's never decreasing, it's always increasing. And this is for all x not equal to 1. At x equal to 1, we have a vertical asymptote. Okay, so now here's information I can use. At x equal to 1, we have a vertical asymptote. So remember, that means the limit as you approach 1 from the right and the left can be positive infinity, can be negative infinity. Okay, so we know that much. And we know that the function is always increasing. Okay, that gives us, okay, let's wait with that. Now we know that the second derivative let's draw this. We know the second derivative is positive when x is less than 1 or x is greater than 3. Now, I don't know where I'm going to just get rid of this y-axis for a minute. Because I don't know where this only gives us information about the shape of the function. We don't have any information about the values of the function anywhere. But we do know that the function's concave up because f double prime is positive when x is less than 1 or x is greater than 3. So we know it's concave up. Okay, here's an idea. That's increasing and concave up for x less than 1. For x greater than 3, we are increasing and concave up. Okay, so if we're increasing and concave up, we've got to be something like, how about we do, I'm not sure where I should put it yet, but I'm just going to put it. It's got to be something like this. Because remember, maybe we should put this in our table. If the first derivative is positive and the second derivative is negative, we're increasing and concave down, so we're like that. Increasing and concave up is going to be like this. That's what we have here. Okay, decreasing and concave down is going to look like this. Decreasing and concave up is going to look like this. Okay, so we know it's going to look like that. Where? I don't know. And then it says for x less than, okay, so between 1 and 3, the second derivative is negative. So that means it's concave down. So maybe we go like that. That's 1, 2, oh, let's go a little farther. So we've got to be going, so between 1 and 3, it's concave down. Okay, so it's got to be like that, concave down and increasing. Okay, and then for x, okay, this is 1, so we can keep going. We can just go like this. Okay, that fits. So you see, I'm just taking each piece and trying to figure out what goes together and then connect them. So this is concave up and increasing down here. This is concave down, and at approximately, so this is concave down between 1 and 3, and then for bigger than 3, it's concave up. So that's, now where you can have an infinite number of possible graphs, but it's got to be increasing concave up, vertical asymptote, increasing concave down, increasing concave up. So we know the shape. We don't know the function values, so we know but we know the shape. So that's number 24. I'll be back with more.